we'll start with something very straightforward, like growth and decay. This type of model is typically used for bacterial growth, population growth, I guess you have cooling bodies, decay, radioactive decay. There's a bunch more, but the basic idea is that the rate of change of population, amount of bacteria, the amount of a substance, whatever, is going to vary proportionally with the current amount of whatever. And the IVP would be written as usually some initial time value gives you some initial value x naught. Okay. This is the model for growth and decay. Here is an example. Let's say we have a culture has N naught bacteria initially. At t equals 1 hour, they are 2.5 times as many, so 2.5 naught bacteria. Assuming the rate of growth is proportional to the number of bacteria present, here's the ultimate question. Determine the time necessary for the bacteria to quintuple. Okay, so I'm going to write down what we know.
Quintuple the original value?
Yes, the original value. Yes. Yes. So we know that initially we have N naught. After an hour, we have 2.5 times that value. And we do know that the rate of change varies proportionally with the amount present. So we have the model dn dt equals k times n. All right, so if you haven't seen the theme, we're going to write some models for scenarios, applications. Typically, they will be types of equations that we know how to solve now. I think before we just wrote models and said, oh, look, there's an equation, great. And then we kept moving on, didn't really solve anything. Well, now we're actually going to solve it. How do we solve this kind of equation? Separation of variables. So we have dn over n equals k dt. Integrate both sides. We get natural log n equals kt plus c. You can exponentiate both sides. So we have n equals e to the kt times e to the c, which we'll call c1. So then here's the solution. And now we can kind of use the conditions that we have to figure this out. So let's see. At t equals 0, we know that n naught, or n of 0 is n naught. So if I plug in 0 into the equation, we get that c1 e to the 0 is n naught. In other words, c1 is n naught. So that means that the solution for this particular differential equation is n equals n naught e to the kt, which should look familiar. You've seen that before, right? It's the general growth law that you probably talked a lot about in pre-calc, and maybe last year even in calc. Yeah, Pert, the shampoo, quality stuff. Okay. So now what do? We also know that at t equals 1, we have n of 1 equals 5 over 2 times n naught. So if I plug in 1, we get n naught e to the k equals 5 over 2 times n naught. Cancel out. Yep, so e to the k is 5 over 2. Take the natural log, both sides, or put it in log form, however you want to do it. Now we get the constant of growth, which is natural log of 5 over 2. Okay, so I don't know if you remember, but usually as long as you have the constant of decay or the growth constant, then you can answer any question you need to answer. How long it takes to double, triple, reach a particular amount, or how much there will be after 7 hours, whatever the case is. All right, so once we have this, yes, sorry. Now we can solve. So what was the question? We wanted to have, so when is there 5 times n naught, right? So we said 5 times n naught equal to n naught e to the k, which we now know is natural log of 5 halves, t. Initial amount cancels. Yeah, I mean, what do we get here? If I want to solve for t, you're going to have to natural log both sides?
Yeah.
You could take the 5 out.
Yeah, I mean, we can do that first, I guess. So that's just going to be 5 over 2 t?
Wait, what?
Isn't it?
Or 2 to the t, sorry. Yep.
Could you like go over the height thing?
Would it be?
Oh,
it would be
now I
5
get
halves e to
That
the
makes
t.
sense.
Oh,
Yeah,
okay, I get
We
it.
still have an e to the t in here too, don't we?
Yeah, the natural
If you
log,
split it up, it's like
I
this.
didn't see that.
Same.
I get it.
No, it's not to the t. It's just 5
it's
halves.
e to the t.
It's just this. This equals 5 halves,
All of 5 percent here
right?
Oh,
Yeah, it'd have to be addition so that you can do it like this. If it was added, then it'd be e to the natural log 5 halves times e to the t. Is that what you were thinking?
Yeah.
Okay. So now we can put it in natural log form. Or take the natural log of both sides, however you want to do it. Bring the t in front. So then t will be ln 5 over ln of 5 halves, whatever that is. And at this point, your calculator will give you a good, what is it? 1.76 hours approximately. Okay. Okay. No, you just magically
You never
knew.
know.
Any questions on that? Okay. Half-life and carbon dating are pretty much the same thing. The only difference is that instead of growth, it becomes decay. The growth constant, instead of being, where was it? Yeah, natural log of 5/2 will be small positive number. Usually, not usually, all the time if it's decay, this growth constant should be negative actually. Okay, so that's the only thing that changes. Do we need to review Half-Life, or do you guys remember those? Okay. We'll just set it up at least. We have a radioactive substance. Decays, usually. So that after 10 years, 1.3% has decayed. Find half-life. And again, this is assuming the usual. I'm not going to write all that out again. Assuming that it varies proportionally with the amount present at time t. So dA dt is going to equal, well, it doesn't matter what variable, I use a, equals k times a. Initial amount, we're going to call a naught. If it's okay with you, we know the solution to it. In fact, if you want to just remember it like you did in pre-calc, the solution is same as before. And now, to find the half-life, that just means figure out how long it will take for there to be half of what we started with.
So we'll have
Eventually, yes. That's what we want to finish with. We have to use what we know, though, to find the constant. We always got to find the constant. So if 1.3 has decayed, how much of A is left? So let's do 0.987 A is what's remaining. Let's call it A naught. Sorry. And then A naught e to the kt. And then once, yes, thank you. Plug in 10 for t. So then natural log of 0.987 will equal k times 10, or natural log of 0.987 over 10 is your constant. Once you have the constant, to find the half-life, you set up the equation, what? Half A naught, because that's what we want to be left.
equals
A naught e to the k, which is right there, times t, and then solve. So it's pretty much the same as before, just decreasing instead of increasing. Okay. Good? Okay. Let's move on to two more types of applications here. Let's do Newton's law of cooling. That's a fun one. If you forgot what it was, the premise was that you have some cooling body and then you have some temperature, we'll call T sub m, we'll call this temperature T sub B. So the surrounding temperature is going to be T sub M, and the body temperature is going to be T sub B. And the idea is that the rate at which this body cools is proportional to the difference in temperature. So that's what Newton's law said. So if it's proportional to the difference in temperature, put a constant in there times the difference, and then we should be good. So here's an example. Let's say we have cake taken out of an oven. With temperature initially at 300 degrees. 3 minutes later, oops, no possessive, its temperature is 200 degrees Fahrenheit. How long until it's safe to eat? What does that mean? Let's say 85 degrees. Okay. So let's write the equation, which would be dt d little t. Capital T is the temperature, t little t is time, proportional to temperature of the body. So let's call that's going to be T. The temperature of the surrounding medium, I didn't tell you. Let me tell you. Room temperature is 70. Okay. So then now we can write the equation. T minus 70. Some conditions. We have T of 0 is what? T of 3 is 200.
So is this assuming that the room isn't warm up as well?
Yes, we're just assuming that it's a large enough room that it's negligible. That this little cake will not really affect the temperature. Okay. So let's solve. How do we solve?
Separation.
Separate variables? Okay.
How would you have done it?
I was thinking linear, but that's okay. dt over t minus 70 is going to equal k dt. So then on the left, when we integrate, we get
Natural log of 2 and
equal to kt plus c. So now we have, if we exponentiate both sides, t minus 70 equals
7.
c1 e to the kt, where c1 is e to the c again. So then t is going to be 70 plus c1 e to the kt. So there's our model for what's going on in the room. Why don't you guys finish this from here? Take a minute or two. I mean, it's really the same as the other two. Run on a notebook there, Roman?
Yeah. Struggles too.
Anybody have answers yet?
What is it?
I got stuck at the end.
There it
Yeah, I did. Natural order.
So about 14.4 is what I'm hearing? Okay.
I tried something from 70, 95. I never get 70.
Any questions? BAM is good enough? Alright.
Pretty good.
Do you know what BAM is?
Well,
By algebraic manipulation.
Oh,
Is
those
that
are
a test?
That was boring ass one.
boring. Oh, that's
Carl, this is on YouTube.
That's really good.
Well, you like me bring them up. Hey, that's nothing like third review. That should be the title.
Okay, last example. Mixture of two salt solutions. Hey, you're the guys that wanted to be engineers. Some of you. Differential equations for life, guys.
That's why I put my patients to sleep. So reciting.
Mixture of two salt solutions. This could be any kind of solutions, but the idea is that you have some tank. Well, it's going to be an example, but I have to set it up first. And let's say initially there's 300 gallons of water in here. 50 pounds of salt is dissolved in the tank. And now, yeah,
Nothing ever happened.
well, we're going to pretend that it can. From the tank, we have water, or a mix now, leaving. So the mix leaving,
Wait, is it 50 or 0.5?
50.
Okay.
Sorry, 300 gallons of water, 50 pounds of salt. The mix leaving is at a rate of 2 gallons a minute. And to make things even more interesting, we have stuff being pumped in
Oh my god. So
we have a mix coming in. Concentration is 2 pounds of salt per gallon at a rate of 3 gallons per minute. Okay. And then next to this tank, we have another tank. No, I'm just kidding.
yeah.
But that'll be in a couple of chapters. Seriously.
Someone's spinning into
Well, no, I mean this kind of stuff does happen. I mean, if you picture places that do it like breweries or anything like that, where they have giant vats of stuff, you know. Yeah. We're keeping it safe here. All right. So we have to come up with an equation so that we can determine the amount of salt in the tank at time t. We want to do that, and then we also want to say how much salt
chemistry needs physics.
present after 1 hour.
This is really useful. Wait, could you go up just a little bit? Yeah, that's good.
So we have one magic tank, stuff leaving, stuff coming in, and the goal is to have a differential equation that models the amount of salt present at time t so that we could hopefully use that to figure out how much salt actually is present after an hour. Okay. Let's change colors yet again. Let's start with a basic equation, dA dt. So for me, A is going to be the amount of salt. So this represents the what? The net rate of change for the salt in the tank, yes? We have two ways, well, two things that we have to look at to find the net rate of change. One is we have stuff coming in, right? So that's going to affect the amount of salt in there. And we also have stuff leaving. Okay, so I'm going to call that R1 minus R2 to start. So this is the amount entering, and then the amount leaving is going to be R2. Let's step aside for a second and actually write out, well, what's R1 going to be? So what's the rate of salt here? Well, rate 1, the rate coming in is, bless you, was at what rate? 3 gallons a minute? So 3 gallons a minute And now the concentration was 2 pounds per gallon. So if I multiply, this actually gives me the rate of salt coming in, yes? Which is 6 pounds per minute. Let's look at rate 2. Rate 2 is leaving at 2 gallons a minute. And the concentration of salt leaving, yep, it's whatever A is, divided by the total number of gallons in the tank, which at time t would be.
Why is it 8 pounds? Why can't you say?
Because the concentration of the tank is changing.
By how much? That's what I'm saying.
Oh,
It's not just divided by 300 because
It's by 1 gallon a minute.
it's changing by 1 gallon a minute. So how do we write that? 300 plus T gallons. Very good.
So this thing will overflow? This thing's
We're
gonna-
assuming there's enough volume to accompany this. Or maybe there's an automatic switch that just shuts it down if it gets too full.
Okay.
Okay.
How did you come up with that 300 plus T?
You did it.
Oh,
Because there's
that
300.
makes
There's
sense.
300 gallons initially, right?
I expect
Yeah.
And then as each minute goes by, if we have 2 gallons coming in, or I'm sorry, 3 gallons coming in and 2 gallons leaving, it's increasing at 1 gallon a minute, so 1 times T. So then the net rate leaving is 2A over 300 plus T, and that's pounds per minute. So now we are in good shape. So let's write the equation. dA dt, we said was going to be R1 minus R2, so that'll just be, and I'm going to drop the units now, 6 minus 2A over 300 plus T. And we did have an initial condition. At time 0, we said we dissolved 50 pounds of salt. So this is what we're solving now. All that work, now we have our equation, we can find the solution for it, and then answer the question, how much salt is left after an hour. Okay, so for this one, how do you guys want to solve it? Linear? So let's put it in the good linear format.
Would it work with separation variables too?
Would it work with separation of variables? Well, you'd have to move the dt over, but then you have the 2a here.
No?
Linear. That's probably the best way to go.
Are you sure? Yeah, well,
Do you see a way to separate it?
no, I don't.
Try it.
I don't.
Okay. So move the 2a over 300 plus t. And then we have that equal to 6. Mu, integrating factor, is going to be e to the coefficient of a, right? So the integral of 2 over 300 plus t dt. So that's 2 ln 300 plus t, which essentially becomes, yes, 300 plus t squared. So now we take the integrating factor, multiply it to the left side. This will just become 300 plus t to the first. Not that you need to simplify it. point of this is that the left side is now going to be the derivative of 300 plus t squared times a, and that's going to equal the right side. Integrate, so now we get 300 plus t squared times a equals, the integral of this side would be 2 times 300 plus t cubed. We can move this coefficient of a to the right, so that a is going to be, oh, forgot my constant. Don't forget the constant. We move the coefficient over, so then that's going to be 2 times 300 plus t to the first, plus c, and then 300 plus t to the minus 2. And now, we know that a of 0 was 50. So plug in 50 when time equals 0. We get 2 times 300 plus c over 300 squared, 90,000, right? You guys can help me out if you want. Just doing stuff in my head. What is this? Negative 550? So then this is going to be 495 with 1, 2, 3, 4, 5 zeros. Is that right?
Yeah.
Right, so there's our constant. And now we have our model. So a of t will be 2 plus 300 plus t minus 400, what is that? 49,500,000 times 300 plus t to the minus 2. And then at 1 hour, I mean, this part is easy, right? Plug in 1.
Wait, but isn't this
Shouldn't be
minutes?
60.
Oh,
Because the rates were
yes, absolutely.
What?
Good.
T's of 60.
At 1 hour, t is going to be 60. I have 338. So about 338. Very salty indeed. Or very whatever.
So
Okay.
Wait, so there's going to be 360 gallons of water.